Okay, hello everyone. My name is Ricardo Tellez. I am the CEO of The Construct. I'm giving this live class from Barcelona. And it is my pleasure to work with Dan and with Andrea to prepare this live class for all of you. And I hope that you will enjoy and you will learn a lot about ROS and about self-driving cars. So this is going to be just an introduction. So it's kind of how can you start working on self-driving cars by using ROS? So we are going to give you the tools so you can start and keep working by your own. Okay, so first a few things in order to know how we are going to work. So if you have connected to the video that is live now on YouTube, you will see that there is a chat in there. You can use that chat on the side, on the right-hand side, to ask questions during the live class. And also, if you are on the room, because some people is on the room that is transmitting this at Silicon Valley Robotics, then you can ask them via voice, because I think that I can hear you without a problem there. We have been testing with Dan previously, and it worked correct. So that's the idea. So we do this as dynamic as possible, as less formal as possible, and in order to enjoy and to learn and to practice a lot of ROS today. Great. Then first, what we are going to do first. So what I'm going to do now is to share with you ROSjet. This ROSjet is a kind of a package that contains all the explanations in a notebook. It contains simulations. It contains some ROS code that we are going to use today on the live class. So I'm going to share this with you, and you will have to open it. In order to open, it's very, very simple. You don't have to install anything. So by sharing, how I'm going to share is by providing you with a link. I'm going to put this link on the chat that we have there on the transmission, and then you just have to click there. And this will automatically open in a web browser on your computer, and will give you access to those files. Don't worry, I'm going to show you how to do it on my own screen. So let's start. If there are no questions, then let's start. For this, I'm going to share with you my my screen.
Ricardo, just to let you know, on the live video, it's just showing us. It's showing us.
Okay, yeah, I just realized. So yes, so hello everyone. So that's the first time that you see me while talking. Yeah.
There we go. And then just to let you know, because our internet is a microwave transmission,
yes,
all of the smoke, we've actually got a great connection, but every once in a while there's a lag spike, and so I'll have people, if they have questions or missed something, just let you know in chat to repeat or to let you know. Okay.
Okay, great. Perfect. Then let's start. So hello, everyone. First time that you see me. While I was speaking, we were retransmitting the room at Silicon Valley Robotics. But anyway, let's go. So what I'm going to do now is to share my screen so you can see what I am doing. Let me share with you this. Okay, so what do we have here? So that is the ROS Development Studio. We are going to use the ROS Development Studio, to develop. That is an environment that our company has created for developing ROS programs online using a web browser. And you need to have a free account. So if you haven't created an account yet, please go to the address that I have put it on the chat. It is rosds.online. If you go to that address, you will be able to create a free account. Then here I have a list of all my ROSjets that I have for different things. And today we are going to use this one. It's about self-driving cars with ROS. And how do I do that? Well, that is a ROSjet, what we call a ROSjet, and I'm going to share this with you. And the way of doing this is just by pressing this button here and copying the link that it provides me and sharing this link with you. So I'm going to put this link on the chat. There is a problem with the chat of Hangouts that doesn't allow links very, very long. Then it cuts it. So what I'm going to do is to put it on also on Bitly, the link, and then I have just shortened it. I'm going to copy it, and that's the final one that I'm going to share with you. So I'm putting this link on the chat. So there it is, and what you should see is, so you should see the link and then just press on the link. This automatically will lead you to the ROS Development Studio, and it will show you what is the project and create one copy of this project in your own account. So please go ahead with that and let me know if you have any problem. Once you have the copy, like I have mine here, we are going to open it. So I'm waiting here just a second, just in case that somebody is stuck there. I hope that everybody is following the instructions. There is no problem. I see no questions, so suspect it's okay. Then what I'm going to do is to open the project now. So it says, oh, is this, about that, blah, 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 description. Yeah, I want to open it. Let's go. Okay, here it says, do you want to restore the workspace? I would say no now, and that's it. I say no because you can say yes, and then it will show you the structure of windows that you have on the previous time that you left the ROS Development Studio. But I wanted to start from fresh. And the first thing that it opens automatically is this notebook here. It's a Jupyter notebook. That is the notebook that we are going to use today for this class, and that contains all the instructions, all the material that we are going to go through. And so in case that you would like later to follow it or to share with somebody else, you can share it in the way that I have shown you on the previous screen. So far so good. Any problems?
Still waiting for it to initialize.
Okay, yeah. Okay. There is Alexander on the chat that says everyone. Hello, Alexander. And so we are waiting for the people to initialize the system. Of course, I had already prepared for me, and I was testing, so mine was already open. And in the meantime, let me just tell you that, so that's a notebook that we create for the live classes. This one is about self-driving cars. And in this live class, we are going to use a simulation of a car. It's a Prius car and a city sim also. And both simulations have been created by the Gazebo team. And so we have just compiled and put it in the proper way for doing this live class. And this notebook has been created by Tony Juan, that he was an intern at the Construct, and myself. You can copy this notebook, you can distribute it, and do whatever you want with that notebook. As I shown you before, that it is, wait. So it is here on that screen. If you want to go back to the page of the project, then you can click on this wall icon, and then you will have it here. And then whenever you want to share that project, you can just press this button here and share the link with your colleagues or whoever. Okay, so we have some points at the chat. And Divya says, Divya, yeah, for my Jupyter Notebook, Windows says doesn't exist. Okay, that's strange. So if that is the case, I don't know, I should see your screen, but let's try to do something. Press on the cross here on this window of the Jupyter Notebook, and then go to Tools, then Jupyter Notebook, and then ROS meets self-driving cars, press there. it should open without a problem. Try that, Divya, and let me know. Then Linda Capito says, mine gets stuck in preparing project files. Yeah, it's quite a big project because it contains a lot of files, so it takes a little while. So that is, just be patient, Linda, and let me know if it doesn't open in a few seconds. Vicentes Capito says, nice course. Thank you. Alexander says, I saw some 404 on the Jupyter window. You should be able to close it and reopen it with the tools menu. Yeah, that's it. That's right. Divya, open it now. Okay, great. So we are on business then. Great. Oh, and this logo, I don't understand why it shows like this. Okay, maybe there was a mistake on the copying of the logo. Let me see what happened. Oh, there it is. Okay, it's the rendering of the Jupyter. Okay, so I presume that everybody is running and getting. So what are we going to see today? First, I'm going to talk very briefly about the self-driving car technology, some key points, so you can get an idea what we are talking about. Then we are going to actually, and not to discuss about the challenge, it's about the levels of autonomy. And then we are going to see how to develop in this environment, in the ROS Development Studio, how to start developing for self-driving cars. We are going to see a simulation of a car, a simulation of a city, and we are going to do an exercise on making the car localize by using the GPS that later you can use. Linda is indicating that everything open. Okay, very good. Great. So just one thing, that if you want to use this material later, we are recording this video on YouTube at the same time that it has been sent to you now, and you can replay them later at any time. If you come to this cell that says YouTube video, and then you press the play button here, run the cell, then you will see here that it appears the video of that live class. At present, if I press here, I will see myself. In this case, my screen, because it's the live one, the live feed of this class. But later you will see the whole video in there. I'm not going to do it because I don't want to use the bandwidth for sending and coming back the signal. So, but this is material for you for later. Great. So let's start with how self-driving cars work. So this is a basic structure. It's an image that we have taken from Udacity. And basically, a self-driving car contains the following parts. First part is a part of perception. It's all the sensors that allow the car to detect its environment. Like it could be cameras, radars, lasers, etc. Then there is this is for detecting where the robot, the autonomous car is, and what is around that autonomous car. I mean, the objects, the obstacles, or the traffic signals, and the directions, etc. Then there is a part that is the localization part. This is the part that uses some of the sensors in the robot and other stuff, like, for example, maps or extra information about the area to determine where in the world is the car. That's the localization part. Then once you have that, there is another part that is called the path planning. The path planning is the module in the car that is deciding how to go from one place that is located to another. So that I would say it's the trajectory that the car has to follow. And then finally, we have the control. The controls are actually the signals that are sent to the wheels in order to execute the path that the car has decided that has to follow, and also to take some decisions based on the obstacles that are in front or the traffic situation. If there are other cars around, you cannot turn, or the traffic lights are red, etc. So basically, that's all the parts that contain self-driving cars. are here, are shown in this picture. That's why it's super nice and very compact, very clear. Then this image, for some reason, hasn't rendered correctly. Let me re-render by pressing play. Here it is. So those are the parts of the self-driving car. And now here we have the sensors that a self-driving car is having. And that's interesting because that's the information that we as roboticists, as artificial intelligence engineers, we want to get this information to take the decisions that the autonomous car will do. And that's what we are going to practice here today, basically. So what do we have? We have a GPS sensor. That's the one that provides us the localization. Where in the world is the car? Then we have ultrasonic sensors that are used for detecting obstacles on the sides or on the front of the robot. Then we have a LiDAR that it's also for detecting obstacles around the vehicle, but in many different heights and many different directions, more directions and heights than the ultrasonic sensors. Then we have video cameras that are usually used to detect obstacles or the traffic situation, like the traffic lights or people, if there is people in front, or the vehicles, how they are moving, etc. Then also we have radar sensors for detecting more obstacles. Actually, detecting the obstacles is a very difficult point. And because, well, I haven't worked with autonomous self-driving cars myself, but I have worked with real robots, with human-sized robots. And we brought those type of humanoid robots to the exhibitions where there was a lot of people, a lot of different situations. And one of the problems that we have was to be able to detect all kind of obstacles. And it was impossible. It was impossible. Every time that we went to a different exhibition center, we found new different situations in which the robot was not able to detect the obstacles. And that's a problem. I think that's a problem. I haven't worked with autonomous cars, so I don't know if that is one of the main problems, but that's what I think that is one of the main problems, to detect the obstacles in all the conditions that a self-driving car can detect. That is why they are putting a lot of sensors for detecting obstacles. Then there is another sensor here that is called the odometry. And those are the kind of encoders that the wheels have, so we can see how much the car has moved. And well, here, that's a central computer. That's not a sensor, but it's okay. It's a computer that is processing all the data. Okay, then finally, before we start developing with the ROS, let me explain you the levels of autonomy that have been defined in order to indicate at which level of autonomy a car is. For example, we have the level 0. This is the level of the current cars. So all our cars, except if you have a Tesla, so all of them, they are level 0. Then we have the level 1. It's when you have driving assistance, but only on brakes or steering, but not both at the same time. And one example of this is those cars that have an adaptive cruise control system. Then we have the level 2, where the car can control at the same time brakes and steering, but only under some specific situations. And one example would be those cars that can park automatically. And then we have the level 3, that is the car that is fully autonomous, so it goes by itself, but under some restricted conditions also, larger than the level 2. And but it requires to have a human on watching the wheel in order to take control if something happens, that the young car will indicate. So that would be an example of the Tesla cars, for example. And then we have the level 4, where there is no need of human driver, but it's on a certain weather conditions and in one particular area that the car already knows how it works. For example, you have created the map of your city. Then your car can maneuver completely automatically in your city. But if you go to the city, to the next city to yours, then you will have a problem with that car. So it will be not able to do it. And then level 5 is the one that we are looking for, the full automation. So please, I want to go to Paris from here. So just bring me there. Still far. I think that, in my opinion, is still far, but I don't know. So if some people know is working on autonomous cars, can tell us better. So basically, that's it. The levels of autonomy that define the autonomous cars. Great. So let's start by working with ROS, for self-driving cars. And for that, what we have done is we have prepared a Prius car simulation with some sensors on board. So you can use this simulation in the future in order to do your own experiments with self-driving cars and design your algorithms and test your algorithms on the simulation. That's very useful because you can do a lot of work on simulation just before you move that into a real autonomous car. That is why I believe that using ROS and Gazebo simulations for starting with self-driving cars is a good idea. So in this case, we have those sensors here, a leader, ultrasonic sensors, cameras, and also a planar leader. So this is let's say that this is a 3D leader that has different layers. As you know, a laser can only measure in one plane. That would be this case. And this case, the 16 beams are kind of packed, different lasers at different heights. So you can use this to detect obstacles at different heights from the ground. So that is the model. Let's launch this simulation together. So you follow. I presume that all of you are on this screen. Then let's go and launch the simulation that is included. First, before we launch it, let me show you where you can find the files of this. Okay, so if you go to Tools, then there is here an option that is called IDE. So if you open it, then let me put it here. Here there are several workspaces, and there is one that is called the simulation workspace. On the simulation workspace is where we put all the files related to the simulations that we are going to work with on this ROS jet, on the current one that we are using. So if you open that directory and go to source, you will see here the CitySim TC contains different packages, are ROS packages, ROS Gazebo packages actually, and you can have a look later how they are created. It contains a lot of things that we are not going to talk today. You have them there, so you can explore later. So in this case, on the car demo, there is the Prius description. This is the one that describes this car. Okay, so here is where this code is located, and you can modify, of course. You can come here and open the URDF, for example, and you will get the code here of the URDF, of the whole description of the car with all the sensors and all the frames, etc., and plugins. So now what we are going to do is to open it. For opening, very simple. Let's go to this option here on the top that says Simulations. Then press Select Launch File. So this option allows you to launch different simulations. So you can launch a simulation that is already included in the ROS Development Studio by default. It's all those robots here that you have here. So all of them, you can just press here and then launch. It will launch a simulation with the controllers, everything working for you to start working with that robot. But today we are not going to launch one of the simulations included in the ROS Development Studio. Instead, we are going to launch the simulation that is included in this specific project that I have shared with you. For that, you need to go to this option that says from the simulation workspace, let's select a launch file. If you press here, then you will get this option, and where it says launch file, click in there and select the file that says single car demo.launch. And then press launch. So a new window will appear that will contain the simulation of the car. So we should get something like this in this picture. You have the instructions also here, okay, for later, if you want to repeat or do a class, whatever with this project. So you get the instructions there. Okay, great. So mine is already open. Here you have the log of the simulation while launching, and you can see if there is any problem. In case that you modify the simulation and want to launch it again, and then there is an error, you will see it here. So let me put it down, the simulation log, and let me move away from the car, because we appear just inside the car. And here it is, the car. Okay, so we got it. And I hope that everything is okay in your case also. So now, what is interesting here is that you already have it working and running, and you don't have to do anything. And because having this running, usually it takes some time and then it doesn't work. So now you have it. And also you have it with all the sensors that I mentioned here. So they are publishing at present. And in order to visualize those sensors, let's do one thing first. Let's open RBase and visualize the situation of the sensors in this car. So for that, let's open a terminal and launch the RBase. The terminals are here on the tools. You can go to tools and then select shell. But it says shell. You can select as many shells as you want. So if you need 20, then you can launch 20. Go there and launch 20. In a closed feature, we are going to do a better organization like Terminator, where you can divide on the same shell. But anyway, so we have it here. Then let's launch RBase. So ROS run, RBase. I presume that you already know some of the commands of ROS so that you can manage more or less. But if it's not the case, just tell me on the chat, okay? Hey, I didn't get that command or whatever. Tell me, because the interest here is that everybody follows and can do it by itself. Just watching it makes little interest if you don't practice. Then, so we have launched RBase, but the thing is that RBase generates a new window where the RBase itself is going to be shown, is this window here. So because we are on a web interface, we need to do a small trick. And in order to get the RBase window, we have to go to tools and open the graphical tools. The graphical tools is kind of a workspace where all the windows, extra green windows, Linux windows that we create appear, then we can see them and interact with them. And okay, so I don't understand that message, but anyway, it connected. So before I connect, I continue. There is a question by Divya that says, how do we zoom out in Gazebo? Okay, so I'm using the wheel of the mouse to zoom out and to zoom in. And I think that there is a key for doing it. Yeah, so you can do it if you don't have a wheel. You can do with the right click, and then you move the mouse forward and then the mouse backwards. The problem is that it also appears this menu. Please don't delete the model. Well, it's okay. If you delete the model, it's okay. You can just go to simulations and relaunch it again. No problem. Okay, I hope that Divya is okay with that explanation. Now, let me do one thing. Let me put this window of the graphical tool in bigger, occupying the whole screen. And before, in order to see all the sensors here and the model of the robot, what we are going to do is to use a RBase config file that we have included into this ROS yet. So we only need to go to File and then open config. That is going to save us a lot of time because configuring all the sensors and the model and the TF and it takes a lot of time. So the file, where is located? So we need to go up to home user. Then it is on simulation workspace. Then on source, CTC TC, car demo again, and then RBase. Yeah, we didn't find a more difficult place to put this file, you know? So we were thinking, what is the most difficult place where we can put this config file? And that's the one that we found. That's why maybe next time we'll do it even more difficult. Okay, just joking. Then, okay, so so far so good. Here we have, if you open that file, you should get this configuration where we have the robot, so the self-driving car. We are showing here everything. I mean, there is the frames, all the frames that the car has. We have the 16 layers LiDAR. We have the ultrasound sensors here on the back and on the front. And then the 2D sensors, laser also. And also we have here the cameras. So here on the side, we have the left camera, right camera, and then front and back. So you can check everything here. Okay, when you do your experiments with this self-driving car, you can use this information in order to see if it is detecting, not detecting, what is happening, etc. So there is a trick that you can do. So now I have maximized this window, the graphical tools window. If you press this button here, this icon there, so it minimizes, so you can move it around or do it or your own space, the one that you want. But sometimes that's a little bit confusing, or you want to have more space. Then what you can do is to press this icon here that is kind of a window on top of another window, this icon here. I hope you can see my mouse. And if you press it, then the whole window will be created in a new tab in the browser. So you can work with different tabs. If you have different monitors, then you can assign the tab to a second monitor. I'm not going to do it because otherwise you will not see it on the screen. So I'm going to press this button, and then you see that this has created a new tab here. Okay, so still improving this situation. So we get this message, invalid login, just because the old one is still here. So in order to get this new tab running, I'm going to close this old one. Don't worry, it's just a visualization window. So the RBase is still there, has not died. So I'm going to go back to the tab and press login, and then it's going to show everything, but on a different tab. Yeah, this is something that we are working on, and on the close future, we are going to solve that and make it even easier and smoother. Okay, so we have in this tab the RBase, and in this we have the rest of the environment. And here there are some ogre exceptions. Don't worry about that. No problem. It's about the stupid things, and yeah, it takes a lot of time to prepare everything, and we didn't have the time to finish this, but it's nothing important. So you have all the sensors there with the different topics that you would expect. In order to see all the topics for the sensors, let's open another shell here on the tools, and you can do a ROS topic list. And then you will see all the topics of the TF, for example, of the cameras, different cameras, then many cameras. Then we have also the joint states. We have, this is the odometry, basic odometry from the encoders, and many other things. Okay, so you have all the different sensors. Here, the sonars that I didn't mention. So in those topics, and then you can do your programs accessing those topics, subscribing to them, and then getting the information, and then create your own programs for avoiding obstacles, going through trajectories, or whatever you need, or detecting people on the cameras, for example. So you got that material there. And another thing that is interesting that we have included here is keyboard teleop. So you can move the robot, the car around. And by moving it, then you can put the car into the situation that you would like to have. And so for that, you only need to write this command here, ROS run, ctsim, tc, etc. on another terminal. I'm going to copy and paste it here. So if you launch it, then you will see that you can control the car with those keys here. So if I press I, the robot is moving forward, as you can see. I'm going to press K in order to stop it, because otherwise it will get out of the window. And yeah, so basically you can use this for putting the car in the proper situation that you want to test, and then move forward, move backward, do a turn manually, and you can test the situation that you would like your program to react in front of. That's very convenient. Many times we use it. Another thing is that we haven't seen the detection. So here is an empty space because it's for making it simple. And now you can, for example, add other stuff in the simulation world. If you go to the launch file of this simulation and create a new world with more details, so you can do it by yourself. Just one test, simple test, it would be to add a new obstacle here. For example, let's add a cube here. And then if we go back to the RBase, we should see the detection of the cube here. As you can see, the cube is there, detected by, this is the 16 layers LiDAR, and this is the 2D LiDAR. And also you can see how well, doesn't that RBase representation look like the Back to the Future car? It's only to me that it looks like this. Okay, maybe. Well, anyway, here you can see that it's detected by the sonars here. So you can do your experiments. Also on the front camera, we can see the cube. Yeah, it's a very ugly cube, but it's there. We can do some stuff. Great. So that's the basics. And then let's go to making the robot, to localize the robot, localize itself on the system by using the GPS. Because localizing the robot using the GPS is the most common way of doing localization of an autonomous car. Why? Because, of course, there is the robot is outdoors, and there is the GPS signal that can provide you with the location of the robot. And however, there is a project, a super interesting project that I highly recommend you. If you are really into self-driving cars, then you have to look for the AutoWare project. AutoWare, I don't know if you know this one, but AutoWare, it's open source. Here you can have the software, and it's super cool because it works with ROS, and It's open source. You can download and start using it. And what they have done, it's super crazy, because the people of the project, they have created a map of the city. So they are actually using typical SLAM techniques for localizing the autonomous car in the outdoors in a big city. Well, it's not so big city, but it's a city where the car is moving around and with a lot of streets, etc. So that's another way of doing localization, but that's not the common one, because that's a lot more difficult and it's problematic. So for outdoors, it's a lot easier and simpler if you can use the GPS. So we are going to use that in order to localize the robot. And for that, remember one thing, that on the sensors that we have on this simulation, there is no GPS and there is no IMU, inertial measurement unit. So we need to add this into the simulation in order to be able to localize the robot using GPS. Okay, so let's start by doing that first, modifying the simulation of the car with those sensors. So this is just an exercise, okay, just to make you understand better the different parts and how you will be able to modify when you are on your own out of this class. So it's a very simple exercise, and what we are going to do is to add 2 plugins to the Gazebo model of this Prius car. And here is the code, okay? So let me put it a little bit bigger so it will make more sense. And here we have the code for the plugin of the IMU, and here we have the code for the plugin of the GPS. So you can see that it's basically loading a plugin and then configuring it with some information. I'm not going to go into the detail of this configuration. Just go to this plugin and then you will get all the data, how you have to solve it, how you have to fill it. I have put it here just some that will work. And that's it, as an example. But maybe in your case, you may need to modify some of the data. The same happens here with the IMU. So those are some kind of standard values that they will work in most of the cases. So anyway, where are we going to add those plugins? Well, on the model of the car. And the model of the car is on the Prius URDF file that I mentioned before. So let me show again. So it's on simulation workspace. You have to use the IDE, okay? We are going to use the IDE for editing the file. So go to simulation workspace, then you go to source, then you go to CitySim, then car demo, then you go to Prius description, and finally on the directory of the URDF. There is the file that defines the model, and is the Prius URDF file. Do a double click and then it will open on the side. Here is the one that I have here, and I'm going to increase the size of this letter of the font so you can see. Here there is a lot of code for defining that car because it contains a lot of stuff. And what you have to do is just to go to the end of the file, because we are going to add the plugins just here at the end, where it says, before it says robot. And you can see here that there is a tag called Gazebo that is including, for example, a sonar sensor and the plugin. In this case, we are going to get here inside Gazebo and include all this code that is here on the notebook. You can come here and select from the first Gazebo tag and then drag until the latest Gazebo tag. Do not put the robot because it's already included there. For some reason, it got copied there. So just from one gazebo to the other gazebo. If you copy that and put it here on the file, then we have added just right now the plugins for the IMU and for the GPS. And remember that you have a change. You see this dot here. This is a dot that is indicating that this file has a change. So you have to save explicitly that you want to take this change, then you have to save. And how do you do that? By going to File and doing Save or Control S. So remember that, because otherwise, if you don't do that, then you will not have the changes saved. And when we relaunch the simulation, there will be no IMU or neither GPS. So now there is no dot here, and it means that there are no changes. Okay, great. So we have modified our car, and now what we have to do is to relaunch it in order to get those changes on the new model. So let's do the same procedure. Let's go to Simulation, select Launch File, and press Launch, Single Car Demo. Now, the simulation is going to launch it and get the changes that we have done on the model. And here we have the RBIS, and it's very likely that it will break. So because the ROS core the master ROS core has died, that was the simulation, then I think that is better if we just Control-C on that window, and that's all. And we'll relaunch RBIS later if we need it. So here we have the car. It looks like there was no error here on the simulation log. So we did it properly. If you forgot to include some of the tags, or you copy something that is not correct on the proper position, then the simulation will not appear, and then you will have some signal in there that is indicating that you have done an error. Okay, we have it here, and we can see if the new topics for IMU and GPS are there, being published. So let's do a ROS topic list, for example. And let's see, camera. Okay, NavSat fix. This is the information for the GPS. So we have the GPS working, and here we have the IMU data. Great. So now we have modified, and it's properly working. This. At any point in time, all the changes that you have done to this project, to the files, if you want to keep those changes on the ROSject that I have shared with you, so you want to keep those changes that we have included, for example, the GPS and the IMU plugins, the next time that you want to open this project, this ROSject, you don't want to have to do all this. You want to start with everything already configured. So then in that case, you can press this icon here of the disk of saving. And this, what it will do is to save the whole ROSject with all the modifications that you have done. If you have modified the notebook, for example, then it will save it. If you have modified the code or anything that is on those workspaces, then it will save everything together. So you will have the modifications. So remember to save it. I'm going to save myself just to show you how. It's very simple, but just press save, and that's it. You can change the name. For example, if you want to create another project that is from this one, so you indicate a different name and it will be saved. This project contains a lot of files, so it takes a little bit. Usually it says faster, but anyway, I mean, it was just some seconds of saving. Great. So let's go for the next step. If there are no questions on the chat. Okay. Well, you can put it as far as you have a question, just put it there on the chat. And now, in the step 2, we are going to create a package where we are going to put the code for the localization. Let's create it. Here are the instructions that you can see. First, we have to create a package for that, a ROS package. And now we are going to create control code. The control code means the ROS code that is going to go into the robot. So it's not code that is related to the simulation, but it's code that it would be in the actual self-driving car if we had one. Okay, so for this type of code, we have created the Catkin workspace that we have here. So let me minimize the simulation workspace. So you see that here on top, we have a Catkin workspace. The Catkin workspace is a workspace, the ROS workspace, where we put the code that it will run on the robot. So by doing this distribution, we are separating very, very easily what is the code that goes to the actual robot and what is the code that is related to the simulation. So you don't mix it. And then once you are developing here and you want to transfer to your robot, just get the packages that are here on the source, and that's all. And you don't mix packages with the simulation, with the control code, etc. So that's what we have to do, okay? We have to create the control package on this workspace, Catkin workspace. So for that, we need to use the shell. So for example, this one. Then we have to go first, let's go to the Catkin workspace /source. Remember that any package of ROS that you have to create, it has to be inside the Catkin workspace and source. Then let's use the Catkin create package command. Catkin create package, and then let's put this name. Please copy the same name, because otherwise, maybe later, some of the code that I have included here will not work because it will not find your name. So it's not something important related to ROS. It's just for this live class demo to make it easy. So the name of the package is going to be Prius _ localization. So let's put it here, Prius localization. And then it depends on ROS Pi. So let's do ROS Pi as a dependency. Great. So that has created the package. And here on the Catkin workspace, we can see now that has been created, okay, this package. Now, for the rest, we can use the IDE for creating the other directories or use the shell. So let's go and create the rest of directories that we are going to need. So let's go to inside this package, cd Prius localization, and then we can create a config directory where we are going to put some configuration files, a launch directory where we are going to put the launch files for launching some nodes that we are going to require for the localization, and then the maps directory where we are going to put a map. Okay, so I got all of them created here. Config, launch, map, and source, it was created by default by the system when I created the package. Great. So let's go. Let's continue. So, well, about this launch file is going to be created later on a step later. Let's go with the step number 3, that is to launch the map server. And here we have something that is strange, okay? So it is a GPS-based system, but we have to launch a map server. That means that there is a map in there. So, well, that is yes, but this is only yes because we want to use the navigation stack of ROS and use the move base system in order to move the robot around. And for that, we need to have a map in order to create trajectories. So basically what we are doing is to launching the map server of the ROS navigation stack with an empty map. So the map server is happy. So the map server says, oh, I'm happy because I have a map. So I can do path planning, I can do obstacle avoidance using this map. It's okay, but it's only in order to use the ROS navigation stack for path planning, for move base, etc., etc. So it's a kind of trick. Then the map that we are providing to the map server, as I mentioned, is an empty one. It's just a blank map. And where is this map? Let me show you. I have included here a directory with maps that says maps. So let me close this source in order to not confuse you. So here we have the Catkin workspace, and then we have another directory afterwards that is called maps. In this directory, I have put those two files that are related to the white, the empty map. If you, for example, if you double click on the floor map, PNG, then it will show you here what it contains. And as you can see, it's a blank, is an empty sheet, I would say. So you can close this. So that's a blank map that we are going to use for the map server. And then for that, let's go to source, Catkin workspace source, and copy those files, both those files, the PNG and the YAM. And let's put it inside the other map directory that is inside the Prius localization package. So I'm just selecting and dragging and drop, and now I have them here. Now this directory maps secondary, I don't need it anymore, it's empty now, so I'm going to delete it with right click, then delete. This is just for making it clearer, because otherwise maybe later I will see this project 2 weeks later and I will not remember what was that there, if something was wrong, or so now it's clear. So we have the map, the empty map here. And what we are going to do is to create a launch file for launching and loading this empty map. And the launch file is here, the content of the launch file. And let me check, because I didn't write here. Oh, yeah, sorry, it's here. The name of the file, it has to be that one, star-map-server.launch. So you can go here to the IDE, to the launch directory, and select the launch directory, do a right click, and then to select new file and put that name, start_map_server.launch. Then if you double click on it, it will open here empty, and copy the code here. That is the content of the map server. And I'm going to explain you, okay? Don't worry. We are not going to copy and paste wildly or without paying attention, but I'm going to explain you what it means. It's very, very simple launch file. It says, let's launch from the package map server. Let's launch the map server. And you are going to load the floor map file. That is the map file that we have included here in the maps directory. As you can see, you have to have the same names, because otherwise this copy paste will not work. So Prius localization is the package, directory maps, and the map file. Okay, so that's it, nothing more. Remember to save, okay? Control S or file save here. Okay, so far so good. So we have the map server configured for launching. Then for the actual localization system, we are going to use a package of ROS that is called Robot Localization. So you have here a lot of more information about the robot localization with different links that explain more about it. and it contains a lot of information, and it's quite complex to use it. Okay, so I'm providing you here one configuration that works, that you can use. But if you want to modify that for your own particular case, then I recommend you to go into the documentation. In those links there is a link here, and here is an example of the presentation at the ROSCon of the creator of this. And then it shows an example also. It's quite interesting, the video that explains everything, so you can check it later. And there is another link beneath, I think it's here. Okay, no, it's not more information. Okay. Then I will provide you another one. I thought that I had included this, but I will provide you later. Actually, not later. Is if you look here, robot localization. And yes, for example, this one. So you will see here it is. So this is the robot localization documentation. Here it contains all the data for configuring the robot localization for your own particular case. And it contains a lot of parameters, a lot of config files and options. So let me include this here. And I'm going to shorten it here. And copy and put it there on the chat, so you can have a look later. I thought that I had included this on the notebook, but for some reason, I missed it. What I'm going to do is that I'm going to include it here. So I'm going to edit in real time. I'm going to edit the notebook and put it here, for example, like this. And here the address. And like this, more info about robot localization, for example. Okay. So I have included this with a new link to the other documentation. Okay, so what is a robot localization package? Well, it's a package that performs, it creates a Kalman filter and allows to combine the information of localization from different sources. So it uses a Kalman filter to mix all that information, so you can generate the best localization signal possible by taking into account all the sensors that can provide you information about localization that you have in your robot. For example, you have the GPS, you have the IMU, the wheel encoders, any odometry of any type. Here it says visual, but it could be on any other. And you use a Kalman filter to mix all of them and then generate an odometry information. Actually, it's an odometry information from a world reference frame. And then you have the transformation also that allows you to transform your robot base link into that wall frame. So you can know at any point in time where is your robot based on that wall frame that you have defined. Have a look because it's very, very interesting package. So for configuring this robot localization package, we are going to launch two different instances of robot localization. And one instance is one node that performs the localization of the robot in the map coordinates. And it's the one that computes the transform that I mentioned from map to odometry of the robot. So map is the wall reference frame, and odometry is the odometry frame that you know that the robot, the car, is computing based on his encoders on the wheels. So this is going to do the transformation between the odometry to the map based on the GPS information. So this wall map is like a a whole wall reference frame that it's generated, that position of your robot in that map frame is obtained thanks to the GPS data. And how do we do that? By using the second node that we are going to launch that transforms the GPS data into the map coordinate. So we have two nodes. The first one that maybe I should have put it in the other way around, but the first one that transforms the GPS coordinates to the map coordinate reference frame, and then the other one that performs the transformation between map and odometry. Okay, so let's do that. How do we do this? Well, so for the first case, for the first part, we are going to create this launch file and populate with the following data. Wait a second. Yeah. Let me see a second. Yeah. Okay. Yes. So let's go to the launch directory here, and let's create this file, this launch file that I have indicated here. So let's go to launch, then a new file, and let's call it start localization with GPS or EKF, extended command filter dot launch. Yes, the robot localization can use can do the fusion of the data with the Kalman filter by using an extended Kalman filter or an ascendant Kalman filter. It depends on your application which one to use, so you decide. So in this case, we are using the extended Kalman filter. And here, so I'm opening this file, this new file that I have created, and I'm going to copy and paste the code here. Let me copy, paste, and then I will explain you the code here. Okay. So we have it. Remember to save because there is the dot. So, oops. So save. Yeah. Okay. So what do we have here? We have three parts. This is the launch file that is going to launch everything for localizing the robot using the GPS. And we have three parts, very well differentiated. First one here on the bottom is the map server. This is launching the map server. But actually, it's launching the file that we have created here. It's the star map server.launch. That is the one that launches the map server with the floor map, the empty map. Okay, so that's covered. That's just doing that. Then here we have another launch that is called the NAPSAT. So this launch file, we are going to see below what it is for and how it works. So let me just skip the explanation. Actually, you don't have to understand anything here. Just is launching another launch file that we are going to create below. And now what it is more important in this step is this second part, that is the one that is launching the robot localization node that I mentioned. So it's on the robot localization package. We are launching the extended Kalman filter localization node. And this is the one node that is going to launch one of those squares here. Okay, so this square here, this is EKF localization node. And this is the one that is going to mix the information from the IMU and from the odometry generated by the GPS and also by the own robot. By combining all that, we are going to create a better odometry. And that is what we are going to do by launching this here. Then the other one here that I have skipped, let me just give you a few data, is the one that we are going to launch here, where we are going to transform the GPS data into some information that can generate the transformation between the map and the odometry. So this is the other node that we are going to launch that uses this GPS information together with the IMU also, and generate this transformation on the TF that allow us to transform wall coordinates into odom coordinates. There is a question here by Alexander. I believe there is a small typo in Jupyter Notebook in the localization with GPS YAM config file. Step 4. Okay. Yeah, it's possible. Yes. So localization with GPS YAM. Okay, I don't see it. Maybe it's on the. Okay, so I don't see that error. You say step 4, an extraneous quote character in the line, process strange character quote in the line. Yeah, it's possible, but I cannot see it.
Right under where your mouse is right now.
Okay, sorry. Where?
Under the.
Oh, yeah, I can see here. Is that one?
Yeah.
Okay. Yes, that's right. Thank you, Alexander, and thank you for the support in the room. Thank you. Just one thing. There is a delay between what I am saying and what is happening in the chat. So the chat and the room, it's faster than my transmission, because my transmission is getting through the YouTube servers, and then it has some delay. So sometimes it's difficult to understand what we are talking about. But yeah, we got it. Okay, thank you, Alexander. So that's it. The change, let me save it for later so we don't keep this error. Okay, so yeah, so we were about launching this and the config file. So what we need to do is to create this config file. This configuration file, we are going to put it here on the config directory. So let's go to the config directory, create a new file. Let's call it, like it's mentioned, localization with GPS.yam. And let's open it and copy the content that is included here. So what is this content doing? I'm doing Control-A to select everything in the cell, and Control-C to copy, and then Control-V. But if you don't know about those commands, then you can just drag and drop and copy, etc. So what is this configuration file? This is the configuration file that is indicating to the Kalman filter which one is the information that it has to take into account and how it has to be mixed. Okay, so basically it's telling, take the odometry that is being generated by the car directly and mix it with the IMU data and with the odometry generated by the GPS. And then take into account the following frame. So our odometry frame is going to be the odom, the base link frame is going to be the base link, and the wall map frame are the same. It means the wall reference frame is going to be the map. Then we have those covariance noise covariance matrices that you can try to optimize this for your specific case. Actually, in simulation, I have always used this in simulation. I've never touched those values that are the default ones. And in case that you would like to touch them and see how to better model your noises and covariances of your different sensors, you can go to this to this information, and then it explains how to do it. I mean, it's a little bit difficult to understand how they explain, but it's the better information that you can have in order to tune that information of the covariances. Then another thing that we have here is this config for each one of the sources of information of data for the position, for the odometry that we want to compute. And this matrix, what it's actually saying is, listen, from the data that you are providing here in this topic, then which components of that data are we going to take into account in order to mix that information in the Kalman filter. So, and as you can see, it is organized by columns, and the columns means that there are 3 components, and those 3 components means the three components of the position for this, and the 3 components for the orientation. Then we have the 3 components of the velocity, of the linear velocity, and then the 3 components of the angular velocity. And then we have the 3 components of the linear acceleration. So for every data, we are indicating which one is depending on the type of sensor that you are mixing, then you have to indicate which one of those components is the one that is interesting from that sensor in order to be mixed into the Kalman filter. And those are the matrices for those sensors. So once you have that, remember to save. Remember to save, and that's it. So what we have done up to here is we have launched the robot localization, and by launching the robot localization node, we are indicating in this file how to mix the different signals, which signals to mix and how to mix them, and what is the expected results in terms of frames that we have here. That's basically what the robot localization node does here, this node here. Okay, so that's one thing done, and then in the next step, we have to do the conversion from GPS data into odometry. This is the second node of the robot localization package that we are going to launch. The only difference is that in this case, the name of the node is not the robot localization, EKF, what's the name? EKF localization node, but instead is not that one, but instead it's called, what is the name? I don't remember. Let me see. NAP, yeah, that's it. NAPSAT transform node. Okay, so that's the node that we are going to launch that also belongs to the robot localization node. This node, let me repeat, is the second node that we have here. This node here. Okay, it's going to create the odometry based on the GPS information, and we are going to see how it does. So this NAPSAT transform node, what it does is converts first the GPS data into UTM coordinate system, because GPS contains the latitude and altitude, so that's not useful for us as we are in the world that's interested in a 3D world, but in the world that we are moving, that's not useful. For that, in order to take advantage of the GPS data, so it has been invented the Universal Transfer Mercator, UTM, coordinate system. That is a kind of 2-dimensional Cartesian coordinate system for any location on the Earth. So it's translating GPS data into something that is more similar to what we understand by a frame in 2D. So where are we located? And then what we do is, with the nav transform node, is first to convert from GPS to UTM, and then we publish a transform between UTM and map, like in this exercise here. So then we can assign the GPS is going to give us the GPS data. And by means of this nav sub transform node, we are transforming into UTM coordinates. But because there is a transform into map, then any position of the GPS, you can make the transformation into a map in our navigation system, in the reference frame that is using our navigation system. So we can localize our robot by using the GPS into our own map. And once you have that, then you can start using the navigation stack of ROS for going from one place to another. So that's the trick that we are doing here. Okay, so how do we launch this node that does that? Well, so we launch it with this launch file here. And let's go and let's create it. Inside the launch directory, create a new file that is called start navsat. So let's create a new file. Start navsat. Start navsat.launch. And then open it, and let's copy all this here. And remember to save, Control S. And basically, it's doing just that. Launching from the robot localization package, the NavSat transform node. How? With these parameters. And yeah, so these parameters, it depends on the sensor that you are going to use and the location where you're going to be. So it has to have a kind of tuning at the beginning on the first time that you are using this for using this node with your real robot. You should do this tuning and decide which values to do here. If you go to the documentation of the wiki here there is the navsat transform node here. So you will see, and they explain some ways to initialize those data. So I have put in this example some values that they do work for this example, and that's okay. And one thing interesting is this one about broadcast UTM transform. By putting true, then we are going to generate this transformation between map and UTM. And what else? Yeah, well, this node is expecting data from the IMU data, from the GPS data, and from the odometry of the robot itself, the one that is generated by the robot, in this case, by the car. So those are the three topics. This is a remap, probably you already know. So the actual name that the car is publishing is this one, and this one. But the code, the navsat stat, the navsat transform node is expecting those other names. So that's what we do in the remap. That's only this, what it does. Okay, so we have the node that will transform signals from GPS to odometry. And that's it. We have everything in there. So the only thing that remains is to launch it and see if it works for our car. That should be around here. Where is it? Where it went? Here. Okay, so let's launch it in any of the shells. Let's do a ROS launch, and the package that we have created, Prius localization, and then the name of the star localization. Remember that the launch file that contains the launch of all the nodes that we are going to use for localization. So it's called the start localization with GPS AKF. Okay, let's see if we have written everything properly. And it looks, yes, it looks correct. And now, what can we do? Well, we can, for example, watch it if there is a, let's open a new shell, or one of the others that we had. So this one. Okay, no, I'm going to keep this shell because it's the one that contains the keyboard, and I would like to move it around then afterwards the car. So, and see on RBase. So let's open a new shell. And in this shell, let's launch the RBase. So let's launch RBase. ROS run RBase. So we can see that there is a frame that is called map, and that the position of the robot, of the car, is moving relative to that map. So for that, we need to open here. I already have this open, and I can go to File and Recent Configs. So I can use the recent config that I opened previously in order to see everything. There it is. Now, what else? What are we going to see? So I don't need this. And actually, I don't need the cameras neither, because too much information, I think. So I'm going to remove those cameras. Also, yeah. And yeah, so now if I move into the, so if I move the car, I should see, oh, here it is. I can see now already the map. Let me see. The map frame that is included here. So I think that this one here is the map. Let me check. It looks like a, yeah. So I don't know if you can see here on the screen, but that is the map frame. So that is like the reference frame for any movement that the robot will do. And this map is generated from the GPS information. So you have a global localization system based on the GPS now. So if you move the robot, actually, I'm going to do one thing, okay? So I'm going to close this tab because I want to see RBase at the same time as I move the robot. So let me close this tab and then go back here to my system. And I'm going to open again the graphical tools here. So it's going to open here. And I'm going to see the, yes, so the RBase as I left it. Now, I'm going to move the car using here the keyboard. So I should see the robot moving related to that global reference frame. And that would mean that the localization is correct. So let me move the robot. Remember that if you want to use the keyboard in order to move the robot, you have to have the focus on the window that is the one that contains the program for the keyboard, because otherwise the keys are not redirected to that window. So remember that it has to be like this, blinking. Okay, so now if I press some keys, yeah, so I see the robot moving and the frame that is moving. Wait, let me stop. Why is the frame instead of the robot? Well, probably because the fixed frame is the one of the robot and not of the map. Yeah, so it's the chassis of the robot. So if we change this into map, we should see, okay. Yes, so here it is. And here, so we have here the reference of the map. And then if I move the robot again, I should see the robot moving related to that frame, to the reference frame. Okay, so you can see that the robot is moving related to that frame. So I'm moving to one side, to the other, and turning maybe, yes. Yes, I'm going back to the future. Okay, so that's it for the localization. Let me know if you have any question on the chat. Well, here it says that you can get the odometry filtered here on this topic, and you can get the actual localization of the robot on this topic. So let's go for the final part, that is the one of the city sim that we have included also here in this ROS jet. So if there are no questions, I'm going to move forward. And you can ask the questions at any time, okay, whenever you feel it. And then the next thing that we have is the city sim. The city sim is a simulation of a city. And this is a simulation that has been created by Gazebo team, by the Gazebo team, I mean by the OSRF. And they have put it public, live. And what we have done is to include it here into this project, and also included a car that is ROSified, because the original simulation didn't include a ROSified car. It means that the cars that were here didn't have all the sensors publishing in ROS, all the controllers for the cars, etc. So what we have done is to include in the simulation the Prius that we have here in this empty simulation. And that's it. So let me show you what we have obtained up to now. So the problem is that this simulation is quite heavy because it contains a lot of stuff. It's a large simulation, and it is advised that we close almost everything. So in order to prevent this, that the system collapses. So actually it goes super slow. And then, so let's do one thing. Let's close the RBase by now. And I'm going to discard because I don't want to get that configuration. So I have closed the RBase, and what else did I have? The localization also, we don't need it because now it's not necessary. And now let's launch the simulation. And for that, because it's a simulation that we have included into the project, we can go to simulations, then select launch file, and change this launch file to another one that is called CitySim Simple Demo Launch. And then let's press launch. Okay, so now it's loading the simulation. And in the meantime, I'm going to have some water. I had to take some water because the whiskey was gone already. But it's okay. It's okay. So here it is. Here it is loading. And getting some connecting to the simulator. So what is the purpose of this simulation? Why do we provide here? We provide this simulation so you can test on an environment that is closest to reality. So we have been doing some experiments up to now by doing on an empty simulation with only the car and a GPS of the world. But by using the simulation, you can start doing more complex things like traveling around the different streets, avoiding obstacles, then coordinating with other cars and detecting traffic lights, etc., etc. So that's why we provide it here. Then we have at present some limitations of this simulation, and I'm going to show you why. Something that we are working now, because as you can see, this simulation only works for Gazebo 9. If you go to here to the top right corner, you will see that this project, this ROS jet that we have open, it's for ROS Kinetic and Gazebo 9. And still Gazebo 9 in our system, ROS Development Studio, is something that is still in alpha state, let's say. So there are some things that we still haven't completely figured out and make it work. So as you can see here, for example, in the simulation, so we have the simulation and the car is there. Here, our Prius is here. So we got it. But as you can see, it's a little bit different from the actual picture that we have here. You see that some colors are not seen, some of the streets are not seen. So that is not a problem of the simulation itself, but of this window that is representing the simulation in our system. So this window is not able to render those materials there. So you can see here that for example, the traffic lights in the simulation, you see that is something very strange, like the 3 bulbs of the traffic light that are floating there. But this is just a matter of visualization here. The actual simulation, this one, is already there. So that's why we are providing it, okay? Because you can still work perfectly with that simulation. So if, for example, if you launch this image view on a terminal, you will see that the cameras of the car, they are watching properly what is on the simulation. So let's do it. Let's copy this command to launch an image viewer of one of the cameras of the robot, of the car. So if you copy that command and you open it into one of the shells, copy and paste, and then we launch it. Let me remind you that this is opening a new window on the system. And because it's opening a new window, a new Linux window, we need to, in order to see this window, we need to go to the graphical tools. Here, graphical tools, and then it should show there. If you get that login message, you can press login and that's it. It will do it. And here it is. So you can see that this is the camera that the robot is seeing. So if I move the car, so let me remember where was the car. Yeah, it's here. But actually, this is a different simulation. So I'm going to close this keyboard. I'm going to launch it again. Okay, so now I'm going to move the car from backwards. So you can see that the car is moving. Let me see. So here it is. Yeah, too many windows, okay? I want to show everything in the same window, so too many things. So I'm going to move that one. Here we have the keyboards. Great, and then let's move it. Yeah, there it goes, the car. And you can see that the car is moving in the simulation and the image is being updated. And so as you can see, the cameras are capturing the actual simulation. Something in this visualization that still needs to be improved in our side, in the side of the ROS Development Studio. So you can use this city sim simulation with the Prius car, with completely ROSified, and start testing your algorithms for self-driving cars using ROS all the time. Of course, you can launch RBase if you want also. And in order for the machines to support RBase, then you may need a bigger machine in the ROS Development Studio, the one that is not for free. Maybe, I don't know. You can try. And let me show here that there is these graphical tools. Then we have here RBase, and I'm going to load the previous config. So we should see, yeah, here it is. Let me put it bigger. So here you can see how this car is detecting everything on the everything on the simulation of the city sim. And it's funny, I'm laughing because I can see here there is a car that has crashed some way that is behind. On the back camera we are detecting this. So so that's it from my side. I think that I have provided you a first overview and a first system that you can use to get introduced into the self-driving cars by using ROS. That's a quite fast way of getting into it and studying the different algorithms, the different sensors, and how they are used for detecting different things, like from localization to detecting traffic lights to detecting other vehicles, people, etc. So you can start working with all this material that you have here. And I would like to finish by providing you with some homework. So I have shown you how to localize the robot. So you have created this localization system that is already there. So remember to save, okay? Let's save it. Before anything else, let's save it because we have all packages. So the localization package that we have created. So let's save it and let's make sure that we have it for the next day. So you can use this localization system that you have created for localizing the robot into the city sim, for example. Then my homework is for you is that you have to make the robot navigate on the city. So you have to make the robot move from one point to another while avoiding obstacles. Okay, for that, you should configure the move base of the navigation stack of ROS for that. And that's all. If you want to learn how to do it, I would like to talk to you about, just very briefly, about these online courses that we have about autonomous cars in our academy that is called the Robot Ignite Academy. That's an academy that it works online, and it teaches you with exercises like this in simulations. So, for example, this course is about self-driving cars, and you have a simulation of a city. You have a notebook that explains you and makes you execute different tasks. So you can learn on that code, on that, how to use the sensors, the GPS, obstacles, and how to use the canvas and to interface the canvas with ROS. That's an example. In our academy, we have many other courses that you can have a look for different types of everything related to ROS, manipulation, perception, and everything. And even machine learning with reinforcement learning, etc., etc. So on that course, you can find this situation. Also, we have published some videos in our channel that explain how to do that homework. You will have to look for them, or you can ask me, of course. Of course. So that's it from my side. So if you have any questions, I'll be happy to answer your questions. Let's see. Let me put the chat here on this side so I can see the questions directly. Okay, great. Any question, guys? So far, so good? Have you been able to follow?
Yep. Fully.
Okay, Alexander says no questions. Great, Alexander Reynolds. Great. So, anybody else? Anybody? No questions? I can show you, for example, in the meantime, related to this last assignment that I mentioned, there is this video that I mentioned. It's another live class that we did for ROS Agriculture group. There is a group that is called ROS Agriculture that is about making tractors and other machines for agriculture to work by themselves. So we wanted to make a tractor to move, performing some trajectories by using the GPS. And for that, we did another extra live class like this one. This is for Silicon Valley Robotics, and the other one was for ROS Agriculture. And in that class, we showed how to capture some points so the robot, the tractor, can later follow the trajectory defined by those points. And it's called, the live class is the number 2. So if you look for extra live class 2, you will see the explanation for that. Then Linda is asking, is it possible to spawn more than one vehicle in CitySim? Yes, no problem. You can spawn them. You have to take into account that when you spawn them, then you have to spawn every one of the cars into a different namespace, because otherwise the topics of the 2 cars will interfere between them because they will have the same name. So for instance, the front camera on this car that we have spawned there, it's going to be called front camera, like this, for example. Then if you spawn a second vehicle, will have the same name, front camera. So both vehicles will be publishing the same exact information. So sorry, on the same topic, different information. So it's going to confuse the system and you are not going to get anything correctly. So how do you solve that? By spawning each one of the robots, of the cars, with a different namespace. How do you do that? Okay, so there is another video that we explain that for drones. So you have, let me check this for you. I'm going to check it for you. So I can provide you inside the class and you will get all the information on this class. But there is another problem in Gazebo by spawning more cars. And the problem is that Gazebo is quite heavy in simulation. So if this city with one single car, it's going so slow, as you have seen, then putting more cars is going to make it slower and slower. So that's something that you have to take into account. One of the things that you can do, for example, to avoid that, is to spawn in order to spawn these cars, is that the second car doesn't have any sensor or any camera. It's just a car that you move artificially by defining a gazebo trajectory points. And then that's going to be not very heavy in terms of simulation, because it will have not to render the 4 cameras, the 8 sensors, the 16 layers of the laser for those. So you concentrate on your car and you put the others moving in fixed trajectories so they can interfere with your own car. So how to spawn with different namespaces is here the video of YouTube. It's about how to spawn multiple robots and separate into different namespaces. Any other question? guys? So, yes. Let me see. Any other question related to the extra live class? Now that I have started, so I'm going to do it for you also. Extra live class. So one thing is that if you like it, the class, please give us a thumbs up on the video, because that will mean that you like it, the class, and that we have done a good job in preparing everything. So if you don't mind. So here it is, the extra live class. I got it. And let me share this code with you. Okay, Linda, my pleasure. Linda says thank you. Yes. So that second video that I have put on the chat is about how to make a GPS-based robot move following a trajectory. Felix says big thumbs up. Thank you, Gloria. Thank you. And well, I don't know, Dan, what is the plan? So I would suggest that if there are no more questions, then we can stop here. What do you think? Let me switch to the camera, to the space. So is Dan around there?
Yep, so yeah, everyone just left.
Okay.
A few minutes ago.
Okay, also I can explain you some things about here. So yes, it's a little bit cold. Yes, those are interesting things that I can explain you. Yeah, tomorrow is Friday. And I don't know what else. So I can dance something. But...
Yeah, I think we're good.
Hey, guys, there. So did you follow? I can see you now. Did you follow? Yeah. Okay. 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 So I think that we should stop here. And in case that you would like to have, you have some more questions or else, you can comment there. Also, I'm going to give you my email here in case that you would like to send me an email with any other questions. And I hope to hear of you or of your super success on the creating autonomous cars in the close future. Maybe we can meet at one of the ROSCon conferences, or when I visit Silicon Valley for the next time. It's going to be in a few months. Yeah. Then Gloria says, I love that we have the YouTube video to go through. This is an excellent setup. Yeah. Yes. And thank you very much for Silicon Valley, especially to Dan for organizing this and for providing the whole setup, because yes, that's very cool. I cannot see it. That would be interesting if somebody takes a picture of this environment and send that to me, because then I can see how it looks in the how you are experiencing from your position. So, yes. Okay, guys. So thank you very much to everyone, and see you the next time. Remember that we are having a live class every Tuesday at 6 CET. Yeah, that's the time, but 6 CET every Tuesday on our YouTube channel. So if you want to attend, and we deal with different subjects, and we follow the same procedure. It's 1 hour. It's shorter, but it's 1 hour. Oh, there is Dan. Hello. Yes.
I'll send you a picture back of the setup here.
Okay, very good. Thank you very much. So anything else? Any other question?
No, I don't think so. Thanks, Ricardo.
Yeah, thank you.
Okay. Thank you very much, guys. See you around the world.
Thanks, Ricardo.
Thank you.
Bye.